We're continuing on with our quantitative study of chemistry. We've learned to relate the masses of compounds to the number of moles and vice versa. Remember what a mole really is. It's just a group of things. We're talking about the numbers of particles involved when we're talking about moles. Now that we've got that fundamental skill taken care of, we can incorporate it into more interesting problems. What we're going to do here is work on ways of expressing the formulas of compounds. And as we do this, remember, it's really important to resist memorizing an approach here. I'm going to make lots of maps to solve these problems. The focus is on being able to develop the map yourself, not to copy my map. So let's just jump right into things and solve some problems. Our first problem today is to calculate the percent composition of a compound. And specific example is, what is the mass percent of each element in aluminum carbonate? So let's think this through. It wants a mass percent. And you're very familiar with the concept of a percentage. If I asked you to if I gave you a bowl of fruit and I asked you to calculate what percentage of the fruit was apples, you'd know how to do that. You would need to know how many of the pieces of fruit were apples and the total number of pieces of fruit. Percent always has that form. In general, where's my pen here? There we go. We can say the percentage is always the part we're interested in over the total times 100%. And again, I'm hoping that makes sense to you, that you can own that in your gut, that you're not going to memorize that either. So if I want to know the mass percent, let's start with a map. What's the part and what's the total? I'm going to start at the end. Well, I'm analyzing a compound here. And I want to know what percentage of this compound is, say, aluminum. What's the percentage of the other elements? I think to do that, I'm missing something. I think I'm going to have to come up with the formula of aluminum carbonate to know what elements are in it. So you might want to pause the video here and write the formula for aluminum carbonate. Based on the charges on the ions, I know that the formula of aluminum carbonate is Al2CO3 3 times. Remember, we balanced the charge on the ions to make the compound neutral overall. So now I can see more clearly what the question is asking me. I want to know what percentage of the compound is aluminum, what percentage is carbon, and what percentage is oxygen. Let's start first with the aluminum. So if I want the mass percent of aluminum in aluminum carbonate, the part I'm interested in is the aluminum, and the total is aluminum carbonate. Now, what about the aluminum? Its volume, its molar mass? Well, the question says I want a mass percent. So the quantities I'm dealing with are masses. I want the mass of aluminum and the mass of aluminum carbonate. All right, as I always do, I'm going to play what do you need to know that? Whoops, get my pen in the right place. What do I need to know that? Well, let's look at the formula itself. On a fundamental level, the formula represents the simplest ratio of atoms in the compound. But individual atoms are too small for us to work with, so we scaled up to a huge number of particles and talked about the concept of moles. The ratio of atoms in the formula is the same as the ratio of moles, so we've just scaled it up. I know there are 2 atoms of aluminum for every formula unit of aluminum carbonate. Similarly, I know there are 2 moles of aluminum for every mole of aluminum carbonate. So if I start knowing how many moles of aluminum there are, and how many moles of aluminum carbonate. If I knew the way to convert from moles to mass, I could solve that problem. I need a conversion factor that has units of both moles and, say, grams. Moles and grams, grams per mole. Oh, that's molar mass. So since I know how to make that leap, I'm ready to go ahead and solve the problem. Well, I'm almost ready. I'd have to know how many moles of aluminum I have, and the question doesn't give me any amounts. But here's the good thing. I'm trying to determine a mass percentage for a compound, and compounds have set composition. So it doesn't matter if I choose a small pile of aluminum carbonate or a big pile of aluminum carbonate. My answer for the formula for the mass percent, will be the same. So I get to choose whatever size I want. You can't go wrong here. If you state your assumption clearly, you're going to be just fine. But I think some choices are easier than others. I think I'm going to choose to consider 1 mole of aluminum carbonate because I know that I can find the mass of 1 mole of aluminum carbonate. The mass of 1 mole is by definition the molar mass. So let's write a clear statement of our starting point. I'm going to choose to consider 1 mole of aluminum carbonate. With that simple consideration, it's easy to know how many moles of the other elements I have. I have in 1 mole of aluminum carbonate, 2 moles of aluminum, 3 moles of carbon, don't forget this 3, and 9 moles of oxygen. So what do I do now? Well, back to my map. If I know how many moles, then my map tells me to find the mass. And here comes dimensional analysis to the rescue. I want to get rid of moles of aluminum and get the mass of aluminum. Now, units first, right? Don't worry about the numbers too soon. I want to work out the units and they tell me what numbers to put in. The other hint I'm going to give you in this case is that we're working with more than one substance. So in addition to putting the units, grams and moles, I'm going to include what substance I'm talking about. Grams of aluminum and moles of aluminum. The units tell me, grams per mole, molar mass, that I go to the periodic table for the number. And that was 26.98, but the periodic table has no units in it. So you got to remember the meaning of it. That is the mass of 1 mole. Molar mass is the mass of 1 mole. So I'm going to put 26.98 grams of aluminum in the numerator. Moles of aluminum in the numerator cancels moles of aluminum in the denominator, and I am left with 53.96 grams of aluminum. Do yourself a favor and show the substances. Similarly, now that I've seen the logic laid out once, it's going to be quicker to do it for the other ones. I'm going to cancel out moles of carbon in the denominator, put grams in the numerator. The units tell me to get that conversion factor, the molar mass, the mass of 1 mole from the periodic table. Don't memorize molar masses. I wish I could unknow that. It's just been a while now. And finally, I'm going to use the molar mass of oxygen to calculate the mass of oxygen in 1 mole of this compound. That is 144.0 grams of oxygen. Now, when you're solving a multi-step problem, you can get lost. I'm going to go back to my map and see where I am. My map told me that in addition to the mass of aluminum, and carbon and oxygen to calculate their percentages, I'm going to need the mass of the compound, aluminum carbonate. And now, with the work I've already done, that's going to be pretty easy. All I have to do is add up the masses of the compounds, and I'll get the molar mass of the elements, and I'll get the molar mass of the compound. And 234.0 grams of aluminum carbonate in 1 mole. Significant figures aren't the most important thing here, but since we've learned them recently, I'll bring it back to your attention. This problem is the kind of problem you're going to slip up if you ever do, because it's got both kinds of operations in it. I've done a multiplication to get the masses of the aluminum, carbon, and oxygen, so I counted the total number of significant figures. But now that I'm adding the values up to get the molar mass, I'm limited by where the number ends. Because the mass of oxygen ends in the 10th place, I'm limited to the 10th place in the aluminum carbonate. All right, so I've got the masses. Now, where does my map say I'm going now? Actually, I started my map too far back. The question part of the question, which is where I should always start, is that I want to find the mass percent. Whoops. So I was really trying to end up down here with the percent of aluminum and the percent of carbon and the percent of oxygen. So I'm ready to go on. I'm going to find first the percent aluminum. And I remember, I didn't memorize because it makes sense to me, that the percentage of anything is the mass of that thing, the mass of aluminum that we found from the previous slide, 53.96 grams of aluminum, divided by the mass of the total, the whole compound, aluminum carbonate, which we also found on the previous slide. And to make it a percentage, I'm going to multiply by 100%. I got my calculator at hand here. 53.96 divided by 234 times 100 is 23.1% aluminum. Oops, lost a significant figure. That's 23.06. Now we have a choice from here. This is kind of a repetitive question. I want the percent of carbon and the percent of oxygen. The question said I want the mass percentage of all the elements in there. You have a choice. When you write a solution for me, you're going to present your logic clearly the first time. I want to see your calculation, like mine, for the percentage of aluminum in the compound. But now that I've seen your logic, you have a choice. You can show the full calculation for the percent of carbon if you like, or because I've seen your logic before, you can simply tap out the numbers on your calculator and write down your result. I'm going to do that. I hope that you have tried to get ahead of me and found out that these are the results. When we're done, we always like to check and see that our results make sense. Some questions won't let you do that, but this kind of problem will. When I have the percentages of all the elements, it makes sense to me that they should add up to 100%. So let's just add them up as a kind of a double check. 23.06 plus 15.40 plus 61.54, and I'm adding here, so I'm going to end in the 100th place. Woohoo! We added up to 100%. Now that doesn't guarantee we're right, but it's certainly more reassuring than if it hadn't. So let me summarize what we've done in this problem to find the mass percent. Because the formula is a ratio of atoms, it's also the ratio of moles. And we know how to convert moles to mass. The moles to mass conversion was the central part of this problem. Now, why do we care? This is a useful problem, but I think perhaps a more useful problem is going the other way. If I knew the mass percent, could I go the other way and find the formula? So that's what we're going to do in the next example. We're going to calculate an empirical formula for a compound. And you'll remember an empirical formula is the simplest ratio of atoms in a compound. Empirical has a dual meaning though. Empirical means based on data. So I'm going to show you how that data turns into the ratio, the smallest ratio of atoms. Here's an example. Our compound is found to be 70.57% carbon and 5.92% hydrogen by mass. The rest is oxygen. What is the empirical formula? Now, you probably solved this problem in high school, and there's a good chance for me to show you that memorizing usually doesn't work. If you try to reach into your brain and remember or have memorized a routine for solving this problem, you're going to feel frustrated now. But fortunately, we don't memorize things, we think. So remember, the focus on here is practicing how to make a map, how to solve the problem, and not the answer itself. All right, this time I'm going to do it right. What's the question part of the question? The question is to find the empirical formula. So that's where my map's going to end. Do you have to make a map? You never have to make a map, but you don't have to answer the question either. I think this is going to be a really useful skill. So I'm going to play what do you need to know that? And when I do that, I keep it as simple as possible, by definition if I can. The definition of an empirical formula is that it's the ratio of atoms in the compound. All right. Now, how am I going to do that? But maybe I'll play what do I need to know that. But I also want to show you that you don't have to be able to keep this thought process going linearly. You don't have to go a step at a time. If you get stuck in one direction, maybe you'll change gears and try it from the other end. What I know about this question is that I'm given the mass percent. In other words, I am relating the masses of the elements, grams of carbon to grams of hydrogen to grams of oxygen. All right. The lovely thing about making these maps is you don't have to see the whole picture at once, but the more you write down, it's amazing. It's like you're not the one that proposed it. You'll start to see a link between things. So how do I relate the masses of things to the ratio of the particles? I know a conversion factor relating masses to moles, which are groups of particles. So if I knew the moles of hydrogen, moles of of carbon and moles of oxygen, the ratio of moles is the same thing as the ratio of atoms. So all I have to do to finish this, to be able to go from beginning to the end, is know the way to get from mass to moles. And do I know that? Well, I need a conversion factor with units of grams and moles in it. Moles and grams, grams and moles, molar mass. I'm set. All right, so for me, that's the important part of the problem, planning it. Now we've got a map. It's just a mathematical follow-up here. So I need to know the masses of carbon, hydrogen, and oxygen from the mass percent. I don't know the absolute masses of these things, but I'm going to use the strategy we used in the previous problem. The formula for a compound doesn't depend on how much you have. You can have a big pile of compound or a little pile. The formula is the same. This is another case where we get to choose how much compound we're going to consider. Any amount will work as long as you're consistent. But since I'm given the amounts in percents, I think I'm going to choose to consider 100 grams. And I'm going to state that clearly, both for myself, because the longer the problem gets, the more you'll want to be reminded of what your first thought was. But also, remember, when you're writing a solution, your job is to be clear enough to teach a reader who doesn't know what's going on. All right, now since I have 100 grams of compound and I have percentages, it's easy to see then that the mass of carbon would be 70.57% of 100, or 70.57 grams of carbon. This is a repetitive question with different elements and compounds in it. Again, I want to show what substance I'm talking about, not just the units. I've got 70.57 grams of carbon. Similarly, I've got 5.92 grams of hydrogen. And I hope if you pause, you can come up with the percentage of oxygen. I know that the only elements are carbon, hydrogen, and oxygen, so the total mass has to add up to 100. If I take 100 and I subtract 70.57 minus 5.92 grams, I get 23.51 grams of oxygen left over. All right, good start. We're at the second box in the map. And now I want you to pause the video and make the next step without me. Go all the way to the end if you can. All right, here I keep going along here. So my map says go from grams, get rid of grams of carbon, and get moles of carbon. Units first, don't jump for the numbers. The units tell me what numbers to get. Moles per gram, grams per mole, molar mass, mass of a mole. And the mass of a mole of carbon from the periodic table is 12.01 grams. So grams of carbon in the numerator cancels grams of carbon in the denominator. 70.57 divided by 12.01 to the 4 significant figures I'm allowed is 5.876 moles of carbon. I'm displaying the significant figures I'm allowed to have. Remember, you always have to show at least that many. But I'm going to keep the unrounded value in my calculator memory. I'm going to store in memory 1 on my Texas Instruments. I think on your Sharps, you have memories A, B, C, and D. All right, so now that I've seen the logic for the carbon, finding the moles of the other elements is just going to be the same logic. So again, if you haven't already, pause and make sure you get ahead of me. For hydrogen, get rid of grams. Get moles. Oh, I need the molar mass, the mass of, 1 mole of hydrogen. .92 divided by 1.008 to the 3 significant figures I'm allowed, 5.87 moles of hydrogen. And I'm going to store in memory 2 the unrounded value. Finally, for the oxygen, get rid of grams of oxygen. Get moles of oxygen. 1 mole of oxygen atoms has a mass of 16.00 grams. 23.51 divided by 16 is 1.469 moles of oxygen, and I'm going to store that in memory 3. All right, I've finished a big chunk of the problem, so now I'm glad I have a map in front of me. I've got moles. I'm at box number 3 in my map. Now I've got to find the ratio of moles. The numbers I have right now aren't integers, and in every formula you've ever seen, we're representing integral number of atoms. So what I'm going to do is take those moles there and make a ratio and turn it into a ratio of small whole numbers like a formula has. So just copying from the previous slide, what we've found so far is that we have 5.876 moles of carbon to 5.87 moles of hydrogen to 1.469 moles of oxygen. I want a ratio of small whole numbers. So what I kind of do on autopilot is divide them all by the smallest number. When I divide by 1.469 by 1.469, I'm sure I'm going to get a small whole number. That's 1. You remember, if I do the same thing to every part of the ratio, my ratio stays true. Now I've got the unrounded values in my calculator memory. I'm going to pull up those from the memory to save time and avoid round-off error. So recall memory A, recall 1 for me, divided by recall 3 to the correct number of significant figures is 3.999 carbons. Recall 2 divided by recall 3, 4.00 hydrogens. And finally, of course, 1.000 oxygen. I haven't put them as integers yet. These are coming from experimentally determined quantities with uncertainty in them. So I've expressed them with the proper number of significant figures. But now I'm going to make that logical leap to what the formula is. I've got to decide if the 3.999 is really 4 or it's far enough off that it's trying to tell me something. I think plus or minus 1 in the last digit, that's the same thing as 4. So I'm going to say that the empirical formula of the compound is C4H4O. Go back and make sure that we've answered the question part of the question. Yep, we went at the empirical formula and we've got it. So let me remind you of the two meanings of empirical formula. First means it's the simplest ratio of atoms. It is. We put that ratio in lowest terms. That's the simplest ratio of atoms. But the word empirical also means from the data. And that's what we did. We got it from mass data that I'll teach you how to collect in a later problem. So it's an empirical formula. That doesn't tell me what the molecular formula is. When I chose to divide through my ratio by the smallest number, I might have scaled it down too far. I got the ratio in lowest terms, but the molecular formula could be a multiple of that. In other words, the molecular formula could be C4H4O or C8H8O2 if I doubled everything, or C12H12O3 if I tripled everything. The ratio is the same. If I want to know the molecular formula, I'm going to have more information. So let's extend this question to find the molecular formula for the compound using the data from the previous example. The additional piece of information we're going to need is that the molar mass was 136.14 grams per mole for the true formula. What did we find previously? We found that for the empirical formula was C4H4O. And if that were the formula, what the molar mass would be, that's the empirical formula, 4 times 12.01 for the carbon, plus 4 times 1.008 for the hydrogen, plus 16. That's 68.04 grams per mole. So maybe you should pause the video and see if you can figure out the next step before I do. What I see from the numbers here is that the molar mass based on the empirical formula looks like it's about half the molar mass. So I think really the molecular formula would have to have twice the number of atoms or double. But if I can't see it that clearly, I have a system for that. I'm going to take the true molar mass, which is the bigger number, and divide it from the molar mass, calculate it from the empirical formula. Tap that into my calculator. And to the 4 significant figures that I'm allowed, that is 2.000. Indeed, exactly double as I thought. We never know if our answers are right, but there are some things we can check to gain confidence. If you came out to a number that wasn't an integer, you know something went wrong somewhere and you'll have to go back to the beginning and try it again. The molecular formula must be an integral multiple of the empirical formula. So we're ready to finally answer the question. The molecular formula is twice the empirical formula, C8H8O2. And I love a good skeptic. If you added up the molar mass of C8H8O2, I promise you'll get 136.14. But I love a good skeptic. Go ahead and try it. All right, so that's the end of this video. When we come back, we'll talk about moles of solutes in solutions.